Hey, I wanted to do one quick example with Ampere's law, a little bit more of a complicated example than what we did with the very simple one in class on Friday. So in this example, I'm going to have a cable that has some thickness to it. So it has a radius here of r, and this is going to have a current flowing towards us out of the page like this. But it's actually going to be surrounded. This is like a coaxial cable where now in this space it's empty, but then out here we have a bunch of current flowing in the opposite direction. So there's current flowing in to the page throughout this kind of ring, this annulus around this central cable, and it's going. So I'll actually label this inner radius R1 because we'll have an R2 inner radius of this ring and an R3 outer radius of this ring. And so the inner cable carries exactly, I'll say, I naught units out of the page, and then there's exactly I naught return current going back the other direction. So there's I naught coming out of the page down here, and I naught spread evenly throughout this outer ring going into the page as well. So if we want to figure out, say, what amount of current is enclosed as we draw different Amperian loops around here, we'll need to figure out some sort of metric of, say, surface current density, which I'm going to define the surface current density in this inner region and the surface current density in this outer region as some sigma 1 and sigma 2. Sigma 1 will be in this inner cable, sigma 2 will be this outer cable. And for the inner part, if we draw little concentric rings of some radius little r, then all we have to do is, we know that there's I naught distributed evenly among this cable, so it's I naught divided by the full area of that cable. And then we do the same thing out here for this. We have I naught divided by the area of this annulus, which is the difference in the area of the outer circle to the inner circle. So we can say pi r3 squared minus pi r2 squared. And these things are just constants. So as I actually do the work to write out this, I'm just going to use sigma 1 and sigma 2 until it comes time to like maybe write in a final answer or something, and then we could maybe plug in to get it in terms of I naught and R1, R2, R3. Okay, so we have a couple interesting kind of regions that we might need to think about. Say, like, what about when R is less than R1? So we're inside of this inner cable, and I want to know, of course, what the magnetic field strength, that's what all these Ampere's law problems are going to be about, is using current to find some sort of magnetic field strength and perhaps direction. So this first region of interest will be if we're inside of this first cable. And if we are inside of it, the enclosed, if I make some little circle here of some radius little r, the amount of current that's enclosed is just going to be sigma 1 times however much circular radius I'm taking up. So this is the current density times the area to give me some amount of current. And so then I can use Ampere's law. Again, let me write it out. This is a line integral b dot dl or b dot ds or something like that around a closed loop is equal to mu naught I enclosed. And if we write this down here, we know this is I enclosed, so say mu naught sigma 1 pi r squared I enclosed will be equal to the line integral of b dot dl. And we know that if I have the current coming out of the page, that this is going to be wrapping, the B field is going to be going counterclockwise around that amount of current, and so we know the direction, and so if I integrate my line integral counterclockwise around that circle, well, B and dl will always be aligned with each other, and B will be a constant value everywhere along that loop, and so that's kind of one piece. You might think, well, how is the field from all of this stuff going to be affecting that? And that's the power of Ampere's law, is while there is a contribution to the magnetic field from all these different points, it will exactly cancel out. Because of the symmetry of this problem, we only need to care about whatever is enclosed in this Amperian loop. And so we only care about this amount of current, this sigma 1 pi r squared. So now we can just say, well, this breaks down to B times L, where L is the circumference of that loop, which is B times 2 pi r. And so we then find, if we solve for B, divide both sides by 2 pi r, the pi and a factor of r will cancel. We'll get mu naught sigma sorry, one second. Mu naught sigma 1 pi cancels. We get one single factor of r over this 2 there, as we bring that over to the other side. And so what we see is that B increases linearly with the radius, that the magnetic field strength is initially increasing in this first region, so I'll call that region 1. And of course we know it goes counterclockwise like that, which maybe, if we want to call it a vector, we could call it like a theta hat, or maybe a phi hat, whatever this angle is pointing in that direction. Okay, so that is our first region of interest. The second region of interest would be, what if R is between R1 and R2? We're in this space in between these two cables. And this is actually effectively the exact example I did in class, because we know the I enclosed is just I naught, because there's no current in between this space here. And we can do this B dot dl is mu naught I naught, and then this B dot dl again becomes now B times 2 pi r, for the same reasons we had above, because we are ignoring the contributions of all these because they would exactly cancel each other out due to the symmetries and the fact that it's not enclosed in this loop. And so here we would say we just solve for B and get mu naught I over 2 pi r. Again, it's pointing counterclockwise for the same reasons as above, but now we see that B is inversely proportional to R at any radius above R1. Okay, then we can say our third region might be, say, what if R is between R2 and R3? If we have that, we're in this region here, we're somehow inside of this little annulus, and our I enclosed is now going to be, well, we've got I naught enclosed, and now we're going to subtract from that, because this is now current flowing in the opposite direction. Some I naught times the, make sure I'm getting this right. Wow, sorry. Let me back up one tiny step. We're going to subtract from that. We've got this surface mass, or surface charge, or not charge, current density, sigma 2. And then we would just multiply that by whatever area we're enclosing. So if we drew a little loop that's in between these two circles, we would say that we have pi little r squared. Subtract from that pi r2 squared. That would be the area of the little annulus defined by the inner circle r2 and wherever we are, little r, inside that loop. And then this thing is the thing that has that I naught show up. So now we can say that this is I naught, and I'll say 1 minus, and I'll plug in, this becomes pi little r squared minus pi capital R2 squared all over pi R3 squared minus pi R2 squared. That's just plugging in the definition of this sigma 2 and factoring out an I naught that shows up here and inside of the sigma 2 term. Okay, so this is our I enclosed, and it is a function of little r. So as we go from this inner edge where we have capital I naught enclosed to the outer edge where we are then effectively 0, because this little r would become r3, and this denominator exactly equals the numerator, so this is 1 and 1 minus 1. We would have 0 I enclosed once we get out to this part. So we're ramping from I naught to 0 with how much current we're enclosing, and so then we can think about doing this b dot dl again is mu naught I enclosed, which is all this expression, and then the b dot dl again, we are going from a positive, meaning outward, or out of the page, current down to 0. So always this is still going to be wrapping counterclockwise around until it reaches 0, in which case it's now 0 magnitude. And so we can still always do this same trick of saying b dot, or the magnitude of b times 2 pi r circumference, and then solve for b, and then let me write this out. We got mu naught over 2 pi r times all of this expression. I'll put the I naught here. We got 1 minus pi r squared minus pi r2 squared over pi r3 squared minus pi r2 squared, like that. And so this is a little bit more of a slightly more complicated version where we have a more complicated dependence on r here, and that is this final region, or this third region. The final region, though, is what if we have r greater than r3, and this one is extremely easy because I enclosed in this region is 0, and so as a result b equals 0 in this region. So we can see what is the dependence in each one of these different regimes. And then I just plotted these different regions. So here we have all these different expressions. What I'm going to do is just show, here we go. Here, I then created just the kind of radial dependence and set all the things like mu naught, I naught, and all those constants and pi to equal 1. So we just see how this thing varies as a function of radius. And we can see it's increasing linearly up to this point, in which case it starts dropping as 1 over r, and then drops as the more complicated expression down to 0 again, and then anywhere above the like r equals r3 regime, it would just remain exactly equal to 0. But this is how that magnetic field strength would vary within that coaxial wire as we go from 0 to R1, R1 to R2, and R2 to R3. So that's a slightly more complicated version of this Ampere's law problem than the one we were working through in class. Okay, hope that helps. See you guys.